Hello and welcome. This is chapter 4. We are dealing now with types of chemical reactions and solution stoichiometry. So we dealt a lot with stoichiometry last class, or last chapter rather. We looked at how to use different reactants to find the masses of products that are created. And now we're going to do that specifically with product or reactants and products in solution, which just means that they are usually dissolved into water. So first thing though we've got to look at is types of chemical reactions. So we'll dive right in. Again, this is chapter 4, but we'll dive right into the types of chemical reactions. So first thing that I would like for you guys to do is to read that introduction on page 139 of your textbook. It has some nice information for you there, and I want you to go ahead and take a couple minutes to pause and read that. Then come back to this video and watch the rest of it. All right, now that you've gotten that intro under your belt, we're going to look at water, which we call the common solvent. So water is vital for sustaining the reactions that keep us alive. It also affects our lives in many indirect ways by cooling the earth, in automobile engines, and it provides a means of transportation. But if you think about our bodies are, the vast majority of them are made up of water. And the reason for that is that all of our cells, all of our blood, all of our muscles, those things all have to have chemical reactions in them that can only happen in water. So our bodies they have this composition of being mostly water because all the chemical reactions that exist to keep us alive and keep us breathing, keep our muscles firing, everything like that, all those reactions have to occur in water. Now, one of the most valuable properties of water is the ability to dissolve substances. Salt is a substance that if you were to put into water, if you were to sprinkle it in, it would disappear, as we would say. Now, it doesn't actually disappear, but it appears to disappear, right? We've seen that probably happen on more than one occasion, or I remember one instance, actually, that a friend played a prank on me by pouring some salt into my water at a diner, and I drank some salt water, and it was very disgusting, but I could not tell the difference by just looking at the water itself. So I drank it unsuspectingly and regretted it because it was gross. But sugar does the same when you use it in your tea. A much more welcome surprise if there is sugar in your tea than salt in your water. Just a little tip and FYI there. But we have to ask, why does this happen? Though the substance has disappeared, it's still present. You can taste it, even whether the sweetening of your tea is the distinct taste or the distinct taste of salt water, right? You could taste it even though you can't see it. So the question is, what happens when the solid dissolves? Well, water, which is referred to as the common solvent, has a special shape. It's HOH with bond angles of 105 degrees. So we know water is H2O, and oxygen is the central atom there. Those hydrogen atoms are around the oxygen atom, and there is this bent shape on water, and we'll talk a little bit as to why that is also. But this molecule contains those OH bonds, which are covalent, which means they share electrons between the oxygen and hydrogen atoms. However, the electrons are not shared very evenly. We'll look at this more in depth in later chapters, and we've talked about it a little bit already, but for now, oxygen has a greater attraction for electrons, or we call that electronegativity, than the hydrogen atoms do, so the electrons spend more time around the oxygen atoms. This means that the electrons are spending that time around oxygen, and because of this, oxygen has a slightly negative charge, and the hydrogen atoms have a slightly positive charge. We denote that with a little delta oftentimes, so we would have a little delta positive, and delta negative to represent those differing charges. Oh, there you go. See it right there as well. The image represents the charges with delta, which is a partial charge. That's less than the charge of an ionic substance. So when sodium chloride separates into its ions, you have a fully positive sodium ion, and you have a fully negative chloride ion. This delta positive and delta negative is just a partial charge. But because of the unequal distribution of charge, water is polar, which gives it a great ability to dissolve compounds. It has slightly positive and slightly negative ends. An example of an ionic solution dissolving in water is going to be shown right here. And you can observe that the positive ends of the water molecules are attracted to the negatively charged anions, because opposite attracts, and the negative ends are attracted to the positively charged cations. So you can see that the anions are separated by the positive parts of water, and the cations are separated by the negative parts of water. Those opposites attract, and they separate each other. Now, this process is called hydration. So salt ions will fall apart and be surrounded by strong water ion interaction. So the water, those partial positive, partial negative charges, are really attracted to those ions in the ionic solids. Now note that when an ionic substance or a salt dissolves in water, they break up into their individual cations and ions. Similarly, ammonium nitrate dissolves in water to create a solution containing ammonium ions and nitrate ions, as shown by the chemical equation here. You can see that a solid, that arrow would say goes to, it's being put in water at this point, and then it goes to aqueous ammonium ions and aqueous nitrate ions. Note that AQ designates that those ions are hydrated by an unspecified number of water molecules. So that just means there's a lot of water around those ions. Now, ionic substances also have great variation in how soluble they are. As an example, sodium chloride, salt, is incredibly soluble, whereas silver chloride is only slightly soluble. The variation is a result of the attraction that the cations and anions have toward each other, or the forces that hold these substances together. The most important thing to remember right now about solubility is that when an ionic solid dissolves in water, the ions are hydrated and then dispersed, or they move independently. So they are no longer together in this solution. They are on their own. And remember that atoms and ions are going to be far, far too small for us to see with the naked eye, so we will not be able to observe those. But I actually have some salts in the back of the classroom that I had dissolved for another lab previously, and it's pretty interesting because all of that water has since evaporated, and what's left over are just a couple of, just a lot of salt crystals actually, and those salt crystals look a little different. So when you get some time for working, you can go around, they should be on the middle back table, the lab bench back there. You can go look at those ion crystals or the salt crystals that have reformed from the ions that were dissolved in solution. It's really interesting to see how they can dissolve, and then when the water evaporates, they kind of reassociate to one another into solids again. Water could also dissolve non-ionic substances. For example, ethanol is very soluble in water. Beer, wine, and other alcoholic drinks are aqueous solutions of ethanol mixed with other substances. So they are just ethanols separated by water that have been dissolved by water. That begs the question, why is ethanol soluble in water? Well, it's due to its structure. So we're seeing this again, this idea that structure dictates solubility. The molecules always contain this polar OH bond. That's actually why we write it as C2H5OH instead of C2H6O, because it's denoting that we have an OH bond, and that OH bond is very polar. As you can see right here, that polar OH bond is something that water molecules come next to and are actually able to have attractions for, and they separate out those ethanol molecules from one another. Now, it is good to note, though, that not all substances are soluble in water. For example, animal fats, they don't dissolve in pure water because fat molecules are non-polar and don't significantly interact with polar water molecules. So think about if you ever got butter on your hands, or you're trying to rinse butter off a plate or something, you can see actually that the water will bead up around those substances of fat, or another one is like olive oil, different oils, things like that. They are very, very hydrophobic. They're nonpolar, and then because they're nonpolar, they don't interact with water. So water beads up instead. Water is attracted only to itself, not to those nonpolar molecules, and just rolls right off. So you have to use something like, if you do get butter on your hands, you have to use something like soap that will actually interact with those nonpolar molecules, soften up those intermolecular forces between those nonpolar molecules, and then you can rinse that away with water, but water itself won't do it. The general rule here is that like dissolves like. We'll talk about that more in chapter 11. But basically the idea is, if you have a polar substance, it will dissolve a polar substance. If you have a non-polar substance, it will dissolve a non-polar substance. So non-polar fats can be dissolved with non-polar means, but not with polar means. All right, we are in 4.2 now, the nature of aqueous solutions, strong and weak electrolytes. There are two different types of dissolving solutions or solids. As we discussed in chapter 1, a solution is a homogeneous, or the same throughout, mixture. For example, that first sip of coffee as you have out of your mug is the same as the last, but its composition could vary by changing the amount of dissolved substance. So if you have a weak versus a strong pot of coffee, right? So if you make a really, really strong pot of coffee in the morning, all the substances in that pot of coffee are going to be the same. So your first cup is going to be the same as your last cup out of that pot. But if you make your first pot really, really strong, just to get you going in the morning or something, you drink the whole thing, you're wired now, and you're like, man, I just love the flavor of coffee, but I don't need that much caffeine. So you make your second pot, and you just don't put as many grounds in it. Then that second pot will have far less. So it will have a different composition by changing the amount that you dissolved into that liquid. But the entire pot is the same throughout. We'll also consider in this section what happens when a substance, or the solute, is dissolved in liquid water, the solvent. So solutes are the solids that you place into the solvent, the liquid. One beneficial quality of a solution is its electrical conductivity and the ability to conduct an electric current. So this could be checked with a simple electric machine like this. But this experiment basically is how well this solution conducts electricity. So on the right, we see that there are no ions. It's just a pure liquid there. And it does not conduct electricity hardly at all. Electricity is going in one side of the tube that's in there and coming out the other side. And then we have a weak electrolyte with just a few ions in it in that center photo. And it conducts some electricity. You can see that light bulb is trying to come on. It's barely lit up versus the one on the right that's not lit at all. And then we have a strong electrolyte on the left where it conducts electricity very readily, and that light bulb is nice and bright. That type A solution is hydrochloric acid. It's a strong electrolyte. B's is acetic acid, which is a weak electrolyte. And then C is a non-electrolyte. Sucrose is a non-electrolyte. So it's actually not a pure liquid, I should correct myself. But it does not conduct electricity at all. Now, the strength of an electrolyte depends on how many ions are present in a solution. A strong electrolyte dissolves to produce a lot of ions, whereas sugar, which is that sucrose, a non-electrolyte, it dissolves into a solution without ionizing. So you can have something dissolve and not dissolve into ions, but it will not be an electrolyte, right? So that's kind of an important distinction. Electrolytes depend on ions. So even if you're drinking like sports drinks and stuff, if you look on the sides, they often will be like, oh, this has tons of potassium ions, this has tons of this and that ions, sodium ions, whatever it is. Those are the electrolytes we talk about when we're talking about replenishing our body. Our body needs electrolytes to be fully hydrated, to be fully replenished after using our bodies in activities, versus just drinking pure water. but you also can think about those in terms of scientific means. So electrolytes are those things that dissolve as ions in water. Now, a strong electrolyte is a substance in which the molecules completely ionize when it's dissolved in water. There are three kinds of those strong electrolytes. There are soluble salts, strong acids, and strong bases. Now, we typically think of bases and acids being opposite, and when it comes to the pH scale, they kind of are. Bases are measuring the amount of OH ions, and acids are measuring the amount of H plus ions. But they are both very ionized. So a strong acid will have a lot of H plus ions. A strong base will have a lot of OH negative ions, which means those things have a lot of ions in them, right? So even though they're both kind of like measuring different things, they can still be very strong electrolytes. And we'll talk about them right now. But the first one is a soluble salt. Now, a salt is anything that consists of an array of cations and anions that separate and become hydrated when it dissolves. For example, sodium chloride. That's a very typical salt that we think of. You put solid sodium chloride into a beaker, you fill that beaker with water, and the sodium chloride dissolves into its ions that are suspended in that solution. Then we have, and salts can also be other cations mixed with anions as well, but that's a great example. We also have strong acids like hydrochloric acid, nitric acid, and sulfuric acid, and they also dissociate completely. So hydrochloric acid, it separates entirely into its hydrogen and chloride ions. Nitric acid does the same, hydrogen and nitride ions, and then sulfuric acid does hydrogen and oh my goodness, I can't remember that anion's name, but it separates also into its ions as well. Somebody can fact check that for me and comment on this video or something like that. That would be sick. That means that if we have 100 molecules, though, the way that these dissociate says if we have 100 molecules of hydrochloric acid in aqueous solution, it ionizes to say we're going to have 100 hydrogen ions and 100 chloride ions. All of the molecules in that compound dissociate into ions. That's a strong acid. Okay, just like that. There are no hydrogen chloride solid pieces in there anymore. They are all dissociated. Now, a strong acid is also most properly represented as follows because of how the proton actually separates from the acid as it dissociates. If we think about that proton being the H of HA, and that's just saying some acid base or acid anion, we put that in water and we get, normally we think of this as, or we represent this right here as an H plus ion, but what we're actually looking at is an H3O plus ion that is dissolved in water. So we talk about it like this as an H plus ion, but we're actually looking at that H3O, which is called a hydronium ion. That's what we're really measuring with acids. Now let's talk about strong bases. Strong bases are substances in which ions dissociate, leaving hydroxide ions, those OH ions. Sodium hydroxide and potassium hydroxide are examples of common bases, and you can see that when they're put in water, they separate as well. Just like that. So a lot of OH minus ions, and that's what we're really measuring when we're coming to bases. Let's see. Remember that when these strong electrolytes are in aqueous solution, there are millions of water molecules that we assume are present, but we don't physically represent them, right? So these are being constantly surrounded by water molecules, but we're not showing that. It's kind of shown, you can see the lid of the top of this liquid right here. That's kind of representing, hey, there's water. Don't forget there's water, okay? Now, I want to talk about weak electrolytes a little bit also. So a substance that only produces a few ions when it's dissolved in water are weak electrolytes. And most often these are weak acids and bases. Because salts dissociate so fully, we don't really have any weak electrolytes that are made of salts. So instead we have something like acetic acid, which is a weak acid. So also we note that we have HC2H3O2 instead of C2H4O2, similar to how we had that OH earlier. This is indicating that we have an acidic hydrogen that will come off of the other molecule so that when it dissociates, right? And there are 3 non-acidic hydrogen atoms. This acetic acid is a weak acid, meaning it will exist in water mostly as undissociated molecules. Only about 1% actually will dissociate. So only 1 of every 100 acetic acid molecules will actually dissociate into its H plus and C2H3O2 minus ions. Okay, so we've got a lot of other ones, and then just 1 that dissociates into ions. You also can see right here, this is an equilibrium reaction, so that means it could go either direction depending on the environment situations and conditions. It could move in either direction. Okay, so for example, if we had a solution containing 0.1 mole of acetic acid, for every 100 molecules of acetic acid, there are 99 molecules that remain as intact acetic acid, and 1 dissociates to create 1 H plus ion and 1 C2H3O2 ion. So there are a lot more of these than there are of these when we're looking at that. And also, again, note that that double arrow indicates that it can and does occur in either direction. It's an equilibrium reaction, so it can move in either direction. So that's an example of a weak acid. Only part or only some of the molecules dissociate. But let's see. So a weak acid is any acid that dissociates only to a slight extent in aqueous solutions. Okay. There are also weak bases that are weak electrolytes. An example is ammonia. When we dissolve it in water, some of those ammonia ions will become ammonium. Some of those ammonia molecules will become ammonium ions and will also force the water into being hydroxide ions. As you can see, it produces those hydroxide ions. That's kind of the definition of a base. And it does not fully dissociate either, meaning that it's a weak base. So if we had 0.1 mole of NH3 per liter for every 100 molecules of NH3 dissolved, we would have about 1 ammonium ion and 1 hydroxide ion. And there would be 99 ammonia molecules present. Okay, so those things do not fully dissociate. All right, let's look at the chemical reactions that take place. There are many that take place when solutions are mixed. I did want to actually note before we go on, there is a difference between a weak base and a dilute strong base. So when we have strong acids and bases, that is a definition of how many of those molecules dissociate. You could have a very dilute amount of a very strong base or a very strong acid. You could also have a really, really concentrated weak acid. So when we're talking about strong bases and strong acids, we are not talking about the concentration of those. We're not talking about the molarity, which we'll talk about a little bit later. We're not talking about the molarity. We are instead talking about how many of, or what percentage of those molecules will dissociate when dissolved in water or when placed into water. So strong acids and bases almost entirely dissociate. Weak acids and bases barely dissociate. I just wanted to make that point real quick also. Okay, now we can move on to the composition of solutions. So chemical reactions often take place when 2 solutions are mixed. So we can perform stoichiometric calculations on these reactions, but we need to know 2 things. First of all, we need to know the nature of the reaction, which depends on the exact forms of the chemicals when dissolved, and the amounts of chemicals present in the solution, which we express as concentrations. So the concentration of a solution can be described in many different ways, as we'll see later, but at this point we consider only the most commonly used expression, which is this idea of molarity. Now this is different from moles. So this is exactly why I have said don't abbreviate moles as M. You have to abbreviate moles as mole, because M is molarity, and even a lowercase m is something else, right? So molarity is a capital N. We'll talk about this later. You don't need to worry about that, but right now we need to know molarity is a capital N, M. So the definition of molarity is the number of moles of solute per volume of solution. Okay, so we say moles of solute per liters of solution. You can abbreviate this by saying moles per liter. Okay, knowing that you're talking about the solid over the volume of the solution. Okay. So a solution that is 1 molar, that's how we talk about molarity. We say it's 1 molar, or 1.0 capital M. It contains 1 mole of solute in every 1 liter of solution. So 2 molar would contain 2 moles of solute in every mole, or in every liter of solution. Okay. And we know what a mole is, right? A mole is Avogadro's number of a substance. So we know that 1 molar, let's say we have 1 molar hydrochloric acid, that means we have 1 mole of hydrogen chloride ions in 1 liter of solution, okay? And we can perform calculations on this. So the question here says, calculate the molarity of a solution prepared by dissolving 11.5 grams of solid sodium hydroxide in enough water to make 1.5 liters of solution. So remember, molarity is moles per liter. So we have to get, right now we have grams of sodium hydroxide, but we need moles. Well, we are well versed in finding moles from masses, and we can use a MOMA to find the number of moles, so that then we can use moles over liters, right? So how do we find molarity? First thing we have to do is find the moles of sodium hydroxide. We use the MOMA, which is 40 grams of sodium hydroxide in 1 mole of sodium hydroxide, and that tells us that we have 0.288 moles of sodium hydroxide. Well, what do we do next? This formula actually tells us exactly what we need. The idea that moles over liters is molarity tells us how we can calculate for molarity. So we just take the number of moles and divide it by the number of liters. Just like this. So we could see that this solution has approximately 0.192 molar sodium hydroxide. That's how you can find the molarity. Again, we're letting our units guide us. I see that I'm in grams here, and I need moles because I need to get 2 moles per liter. So I could say, all right, this is 0.192. So I can get grams to moles, divide my moles by my volume, the liters, and then I get my number. This is good to note real quick that 0.192 moles of sodium hydroxide can also be written like this: 0.192 moles of sodium hydroxide over 1 liter. Okay, this is another way to write that. So again, anytime I see these kinds of things, I should see these not only as information that is being told to me, but I should also look at that and say, hey, I could use that as a conversion factor. Okay, I could use that to go from moles to volume if I needed to, or from volume to moles if I needed to, right? So that's just a good thing for us to note and be thinking ahead with. Okay, let's look now at the concentration of ions. So the concentration of ions dissociated in 0.5 molar cobalt nitrate. So first of all, what would be the balanced equation for dissolving the ions? Well, if we look at this, we could say, okay, there are 2 nitrate ions and there's 1 cobalt ion. And when those things dissociate, I can assume then that they will fully dissociate because it's a strong salt. And so it will dissociate like this. All right, so for every cobalt nitrate molecule that I put into water, I should have 1 cobalt molecule and 2 nitrate ions, or 1 cobalt ion, and 2 nitrate ions. So then what is the molarity for each ion? I can use some ratios here to figure that out. So cobalt has 1 so its molarity will be just 0.5, and nitrate has 2, so its molarity will be 1 molar. Another way to think about this is to say, okay, I know that I have 0.5 molar cobalt nitrate, and I know that 1 mole, or 1 molar, let's actually say that, 1 molar of cobalt nitrate will dissociate into 2 molar of nitrate ions. So using this, I can actually convert, just like we have before, using this ratio right here, this mole ratio. Because those are both just moles over 1 liter, moles over 1 liter, I could say this is a mole ratio using moles over 1 liter of each substance. Okay, so that's what's actually happening right there. Okay, I should also include sig fig, so 0.50. But I just wanted you to see that that's what's actually happening. Okay, how about the dissociation of 1 molar of iron chlorate? Well, if I were to, and that might actually be perchlorate, but if I were to look at how this dissociates, there are 3 perchlorate anions that dissociate and only 1 iron cation. So when I'm using those mole ratios, I should include a 1-to-1 ratio and then a 1-to-3 ratio. Okay. You can do that to figure out how many. It would be 1 mole of, or 1 molar iron ions and 3 molar perchlorate ions. Now going one step further, you can actually find the number of moles in a solute of a given volume, moles of a solute in a given volume of solvent with molarity. So if it asks you to calculate the number of moles of chloride ions in 1.75 liters of 1.0 times 10 to the negative third molar zinc chloride, well, first we look at this little dissociation reaction, kind of. And then we would say, okay, what's the molarity of chloride ions in that solution? Well, we see that ratio of 2, because 2 chloride ions are produced from every 1 zinc chloride molecule that is dissolved in there. Then I could say, okay, well, how many moles of chloride are there in 1.75 liters of solution? All I have to do is, because I know that molar is moles of chloride over liters of solution, I know that liters and liters are going to cancel off. Boop, boop. And I will have, just like you see in the second portion, boop, boop. And then I will do that multiplication to see how many moles of chloride ions I have. Okay? All right. That is all you need to go based off of this first portion of the lecture in Chapter 4. So your homework will be posted. Go ahead and take a look at that and get started.